we are going to discuss the path existence query in graph 2. And study we have already discussed the part 1, that was this one, and it was simply the array was sorted, right? And the part 1 was that we have given that array was sorted in increasing order, right? And there was a max diff, and we need to just check that uh, U and V belongs to are connected or not. And the edges were same. If the difference is less than equal to max diff, then there is a edge between node I to node J, right? And yesterday we have already seen that uh, if components are if two nodes are in the same component, then they will be always connected, right? And today we are seeing this problem, right? And here as well, it has this question is absolutely same, right? And now we have to the array is not sorted, right? The difference is first is the array is not sorted in this question. Array is not sorted, and now in the queries, right? Now in the queries we have to not only tell, we have to tell the minimum distance between u and v. And if no path exists, then we have to return -1, right? For the every queries, right? And nodes are not weighted, right? So let's go and see the example first, right? So this is the example we have given that nums is given 5, 5, 3, 1, 9, 10, right? This is given, and we have given the match diff as 2, and queries is 0 and 1. So this is 0, right? And this is 1, right? So since the difference is uh, 2, right? So we can reach there, and how many steps? We are just taking one step. So in one step here we have answer. And similarly for the 0 comma 2, right? For 0 comma 2, if you see 0 comma 2, so 0 comma 2 difference is 4, so we cannot go. But we can go here in one step because it is 3, and here the 3 and 1 difference is 2. So in this step, so in total 2 step we are able to reach, right? So for that answer is this. For 2 comma 3, so this is 2 and this is 3, right? But the difference is 8, but max difference would be 2, so we cannot reach here, right? From any nodes, right? We can go here, from any nodes, we cannot reach there. Right? See, it is 9, it is 6, and similarly for 3 comma 4, right? So it is 3 and this is 4. So the difference is just 1, so we can reach here, right? In one step. So answer is 1 here. So the brute force idea, what we are seeing, the brute force is simple. For if you have to check the minimum distance, you can just do the BFS from here, right? Just simple BFS, right? If in how many steps we are reaching from this 0 to 1, right? So in one step we are reaching here. Then for 0 comma 2, if you do the BFS, then when you will do the VFS, so this is one, this is second layer and third layer. So in total 2 steps you are doing. But since the constraints are given as 10 to the power 5 for nums, right? And for the queries also, it is 10 to the power 5. So it is total of 10 to the power 10, which will give us TLE, right? So now see how we can optimize this. Since the since we know that in 90% of the query questions we have to pre-compute it, pre-calculate it, right? Sorry for the lag. Uh, so in we know that in queries questions in the 90% of the cases we have to pre-calculate, right, so that we can do these queries in log n, right, or o of 1, right. So we will see that how we can do that, right. So if you see that from one node, right, the same example we will take here, that this one, right. So it was 531990, right. So it was 5315319 and 0, right. 9 and 10, right. So so from 5 where it can go, it can go to here, right, and 3 can go here, right, and for 9 it can go here, for 10 it can go here, right. So for 1 it it can go here. So from the previous question that we did, we came to know that if we sort this, we will able to find out that if from 1 at max where we can go. For 1, if we sorted, we can just find out the 1 plus the max dip is 3, right? And at max it can go up to 3, right? And from 3 we will add to 5. So we will able to calculate from any index at far most where we can go. So we can, this will be very helpful for us. So the first thing is to do that we will sort this, right? So we are going to sort this. So we will sort this. How we will sort this? Very simple. But uh, since the queries, right? Whatever the queries is given, the queries is, so we are discussing that we need to sort the array so that we can find out from you where at max till what index we can go, right. So if it was sorted, then it will be very helpful. But the queries are, uh, we have to query that we have given index, right, from index of the node, right. So we need to preserve that. So we will make a new vector, right, that will stores the nums I and the index it belongs to, right. And then we make a vector to get index, right, get index, and we will store that after sorting where the nums I belongs to. So if we sort it, that is 5 1. So our array was 5 3 1 9 10, right. So what we will do, we'll make a temporary vector. So it will store 5 comma 0, right, 3 comma 1 and 1 comma 2 and 9 comma 3 and 10 comma 4, and we will sort it, right. So after sorting, what is will become, so it will become 1 comma 2, 3 comma 1, right, 5 comma 0, and it will become 9 comma 3, and it will become 10 comma 9, right. So then we will we will make a vector which will tell me that for if the query is for 0 comma 2, so this will tell me the in the sorted vector what is the index of this 0, right? So we will store that. So we will do nothing. We will store that in a vector, right? So we will traverse from here, right? And we will take this 2, right? So uh, so it is zeroth index, right? So we will fetch this. So it is 2. So we will store for 2 indexes in the sorted vector is 0. Now here we get 1. For 1, the sorting position is 1. For 0, right? It is for 0 it is 2, right? We'll store this. And for 3 it is 3. And for 4, right? For 4 it is 4. So this will tell me for the 0 we will just go here, and here it will tell me the index is 2 in the sorted vector, right? So we will go here and we will check that at max at max till what index I can go, right? So difference was 2, so at max 7 we can go. So from here we can go to 7, so there is no 7, so we cannot go from here, right? And if it was 2, right? For 2 we will just go and check for 2 the index is 0. From here where we can go, right? From this position we can go up to 1 plus 2, right? Up to 3, right? So this is so this is 1, so up to here we can go, right? Up to this position, right? And for 3 we can calculate that, right? This is from 2 we cannot go beyond this, right? In one step, right? In one step. So it is very helpful, right? And now see, you have from you know that one step you can go up to this, right? Suppose the max diff is 10, right? If max diff is 10, right? If max diff is 10, max diff is very big, right? So our array was the sorted array was, right? Our sorted array was 2, 3, 5, 9, 10, right? And suppose the max diff is given as 10, right? And so from here, from 2, we can go up to which positions, right? So from 2 we can go up to 3 because difference is 1. We can also go up to here because difference is 3. We can also go up to here, right? And we can also go up to here. So for this 2, right? For the zeroth index, there is this many edges, right? And similarly for 3, there will be so many edges, right? Similarly for 3 also, it can go here, right? It can go here, it can go here, and it can go here as well, right? So since you are seeing that there is so many edges are there, and this is very messy. One observation we can do that since it is sorted, right? So by gridly, what we do that we will just check that at max in one step up to which index we can go, right? So if we can go up to here, so it is 10 now, the max dB, so it can go up to 12, right? So 12 it will be out of bounds, so the last index we can go is this one, and this was the last index uh, we can go up to. So we can always say that whatever the previous value between this u and this v is there, we can go to all these nodes, right? Because the difference will be smaller than this, right? since array is sorted, right? So so that there were so many edges, but we reduced our. So, and let's suppose max diff is now is 3, right? So we reduce that from this is we can go up to max 5, right? And from 3 we can go up to 6. 3 plus 3 is 6, right? So at max we can go up to here only, right? And from 5 at max we can go to this one only where it was 538, right? And for 9, 3, 12, we can go up to here. For 10, we can go up to 13, right? So this one only. For 12, we can go up to 15, right? And for 2, we can go up to 17. So now you see, we reduced there were so many branching, right? So many edges. But now we have reduced to, so So in one step, right? In one step, 2 can go up to 5, right? 3 can go up to 5, and 5 can go up to 5 only, right? And in 9 can go up to, right? 12, 10 can go up to 12, right? And 12 can go up to 12 only, right? And 15 can go up to 17, and 17 can go up to 17. So you see this, right? The edges has become single edges, right? Right? And if any query comes, right? Suppose if query comes, right? So tell me about this is the number, right? But query comes in the form of node, right? In the indexes. Suppose the query comes that can we go from 0 to 2, right? In how many steps? The minimum steps. So what we will do? We'll just check, right? So there is a direct case we can go. Suppose this query comes that can we go uh, from uh, 3 to 5, right? 2 to 3, right? Query is 2 to 3 means 0, comma 1, right? That index, right? So there is a edge from 0 to 5, right? So in one step, we are able to reach 2, but we are surpassing the target. We are going after the target. We are passing the target, right? We are going beyond the target. This is target. And so since we can in one step we can go, we are passing the target. That means that we will able to reach here as well in one step, right? So in one step we can go here there as well. So thing is, if the if max was, suppose if max was 4, right? Let me give you another example. So what I am telling that if 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 we have to go from U to V, right? From U to V, right? So if it in one step U is beyond V, right? Here is the U and here is the V. Then we need to go more further, right? We have to take another step. But in one step, right? If if you we take one step, but we are somewhere here, right? We not surpass the V. But in one step, if we passing the V, we come somewhere here. So we know that in one step only we can reach here as well, right? Because the difference will be less, and we can always reach. But in this case, in one step we go here, and in the second step when we take, we are coming here. So we know that from here we can reach in to the target in the second step, right? So since uh, so we are doing this, and the brute force will be just checking that from here in one step where we can go, right? So u dash, then u dash to u2 dash, right, in the second step, right? Then u3 dash, right, in third step. Then finally we are reaching or surpassing the our target, right, in the fourth step. So this will take for the Q queries, right? So if the max diff is one, right? If max diff is one, then in that case, the query can go up to 10 to the power 5, right? So each query we will travel taking 10 to the power 5 steps, right? So that will give us a TLE, right? So can we pre-calculate this? So there is a concept called binary lifting, right? So there is a concept called binary lifting. What we uh, the condition for this binary lifting is nothing but the graph should be functional. The first condition is that the graph should be a functional graph. What a functional graph means that for every node, right, the function graph, right, this function graph means that for for every node there should be at max one outgoing edge, right, outgoing edge. This is the only condition to uh, apply binary lifting. So we can apply binary lifting. Now let's understand what binary lifting is, right? So binary lifting is nothing that if you have a graph, right? So it's A, B, C, right? D, right? Now E, F, right? This is the graph. And someone asks you in the third step from A where you can where you from this A node where you will reach in the third step, right? So also there was one mistake here. Since there can be only one is from there can be only one edge from any node. I have mistakenly done that, right? So so there can be only at most one is, right? So if you take the uh, if you go take third step, right, the third successor from node A, where you will reach. So this is the first step, right? You reach B, right, in the first step, and the second step you reach C, right, and in third step you are reaching E, right. Now if I ask you that, okay, in fifth step where you will reach from A, fifth step. So in third we reach here, so in fourth we will reach in fourth we will reach here, right, and in fifth we cannot go, we come here as well, right. So so if instead of going 1 1 1, if I told you that the binary of 3 is what? The binary of 3 is 1, 1, right? So it is 0 to the power 0 and it's 2 to the power 1, right? So it is 2 plus 1, right? Binary, right? Of 3, 3 of binary is 2 plus 1. So can we take two steps? So this is 1 and this 2 step, right? We are taking 2 steps at once, right? We are taking two steps at once and then taking one step, we are able to reach the same node at E where we reach. And suppose for the 5 also, what is binary of 5? That is 101. That is 4 plus 1, right? So from here, if we go take 4 steps, 1, 2, 3, 4. So we are reaching here directly. And if you take one step, it is directing towards itself only, right? So we can see that so any step we can always we can convert any number to binary, right? So for the any kth step, k can be represented in binary, right? So what we will do that whenever things comes like 5, so we will break this in binary and we will take 4 and one step, right? 4 plus 1. So we calculate this that from any node, from node A, if I take 4 steps, where I will reach. And then from here, in one step, we can pre-calculate this, right? So this is the concept of binary lifting, right? Just we have to calculate the from any node, right? Any node into the power I, where we will reach. And this is pretty simple, right? I will show you how. So we already know that uh, for the graph we have seen it above, right? So for the max diff was 3, right? So 2 were able to reach 5, 3 was able to reach 5, I was able to reach 5 only, right? 9 was able to reach 10 and 10 was. So we know that, so we know the successor of 1, right? In one step, right? So what we will do with respect to every node, right? That is 2, this is node 0, right? Node 0, that is 2, right? Let me write only the node only, right? 2, 3, 5, 9, and 10, right? So in one step where I can reach, so we have already pre-calculated that is 5, 5, 5, 10, 10. So if you take from this node one step, from this node, if you take one step, we will able to reach here, right? So now if we take 2 steps, right? Now we have to store for the 2 steps. If we take 2 steps from here, from 2, where I will reach. So 2 step is nothing. If we see here 2, 3, 5, 9, 10. So so we have to take 2 steps from here, right? 2, right? So we have to take 2 steps from here. So we take one step from here at 3. We reach 3 in one step. And from 3, we take one step, right? One step to reach 5, right? Which is total of 2 steps. So can we write like this that uh, 2 step, right? Let me write like uh, up to right from node 2 to take two steps is nothing but taking one step, right? Step from two, right? Taking one step from two, and the node we will reach, right? The node will reach some node, right? And this is not nothing but we reach three, right? And from three, right? So we can just do like this. From three, we take one step, right? So it boils down to, right? Suppose our name is up, right? So up of u, that is node, comma I is nothing but taking to the power I steps. We can write this as we take from u I minus one step, means the half step, right? To the power I minus one, right? That means this. And the node we will reach here. Suppose we reach u dash, right? And uh, we reach u dash, right? And from u dash we take the another half. So it is like y- up u dash I minus one, right? We reach from this node we take the half, right? So for calculating two, half of two is nothing but one. So we take one step from this, we reach three, right? We, we reach u dash three, and from three we take another one step. So this is the formula that comes, right? That is for the up. It, so the transition state is this is up u I minus one and I minus one. So this is the transition state, right? And and what does this up u comma I represents, right? So up is a vector of vector. This is a vector name, right? It states that the it will store the the target node, right? The target node of taking to the power I to the power I steps, right? From node u, from node u, at which node you at which node you will reach, right? That means the target node, right? At which node you will reach, that will be stored in this. So that is pretty simple, right? And so at max, our constraint is 10 to the power 5. So the log of 10 to the power 5 is somewhere around 16, 17, right? 16 to 17. So we will take 20, right? So uh, in the 20 bits, right? In the 20 bits, at first we can represent every number that will come in this, right? So we can easily represent this, right? So at max we need the k value to be to the 20, right? So for every node we will store, so for every node, suppose it is 2 3, right? There is 2 node 2 3. We'll store 1 2 4 4 step 4, then 8 and up to 20, right? So if anyone say if I have to take 10 to the power 5 steps from this node, so this is pretty simple, right? So it will around I will be around 16, right? 16 is almost about 10 to the power 5 around, right? So We just jumps to I16 somewhere really here. We jumps to here and we have already pre-calculated answer for that, right? And and this is just for safety, right? We generally take 20, right? So that we don't have to remember. So this is pretty simple, right? You get the instruction. So now suppose we by doing that we have stored, right? So for any queries, right? Any queries, right? If any queries comes, we will get the index in the sorted array, right? That we have already stored, right? Suppose index comes as L1, index comes as x and y, right? We are stored in a variable that will index, right? And now, since the value at x, since this was the original, right? This is the sorted index, and there can be chances that the value of x can be greater than y. So, but we have only stored from a smaller node to larger node, so we'll swap it, right? We'll swap if the condition is that x is greater than y, right? Nums of x is greater than nums of y. We'll swap x and y, right? Now, what we will do, we'll check that if of x comma 19, right? We have already stored, right? At max 19, or you can take 20, right? So starting from u, right? If you take the to the power 19 steps, can, can are we surpass the our target, right? So if it is less than the y, right? So if we don't surpass our target, that means that it is unreachable. We cannot reach that target ever. That is not in our component because 10 to the power 19 is almost about 10 to the power 8 steps, right? So it is max, it is greater than our constant, right? So if you cannot reach in to the power 90 steps, so if this is the condition, then we just return -1, right? I mean, store answer -1 that we cannot go, right? Now, now if uh, now we know that we can go to our answer. So, but we don't know how many steps we need to take to reach y, right? Node y, right? So what we will do, we will take the steps in the power of 2, and what we'll do that from node u, right? We firstly take to the power 18, 18 steps, right? That we have stored, right? Up U18, right? And if we surpass our target, if we surpass our target, that means there is no need to take 10 to the power 18 steps. We can do it in a smaller only, right? So suppose you take 10 to the power 17, but you still surpass. So you can go furthermore. Suppose you take 10 to the power 16, right? And 10 to the power 16 comes somewhere where here, right? So, oh, let me do it. So, suppose number will not be that much greater, but suppose 16 will also surpass. So, suppose we do like this and at 8, right? At to the power 8, right? at up 8 we count the y is the target we reach before y, right? This is 8, right? In this step we are not able to surpass y, right? So we are not able to surpass y. That means that we have to take at least this much step. So what we will do, we'll add this to our answer, right? That this much step we have to take only, and we will take that u here, right? And now see, in to the power 9 step, right? In to the power 9 earlier we surpassed it, right? And in to the power 8 we are still back. That means that we need less than to the power 8, right? This distance will be less than to the power 8, right? Why? Because if you see, if 2 into 2 to the power 8, it, this will to the power 9, right? But if this distance is to the power 8, this is less than to the power 8. Why? Because if it is less than or greater than, so it should be greater than the to the power 9, which is not the case because in to the power 9 earlier we checked that surpassed that, right? So it will always less. So we add that distance to the power 8, and since this distance will be less than to the power 8, so we will check for to the power 7. Then if we take to the power 7 is surpassed here, right? So there is no need to take that much step. And then again we check for to the power 6, not it also surpassed. Then check for to the power 3, so it comes somewhere here, right? And we take to the power 2, so it also surpass, right? Then take to the power 1 2 steps, so it comes somewhere here, right? It don't surpass. So at the final step we will just the we will be always as previous index of y, right? We will not surpass it or not come to that index. So we will simply return distance for plus 1 in our answer, right? So that is the solution, right? So this question was the mixture of first thing to make was to that uh, observation that needs to solve this question was the first observation was that since ages ages were dependent upon the distance, right? The distances, right? Distance. There was condition, right? Nums I minus nums j should be less than equal to max diff, right? So this tells that we need to sort it so that we can get uh, we can calculate the edges in a more efficient manner. And the second observation was clearly we were checking taking we were considering only the uh, from you the max node we can reach, right? The farthest node, right? The farthest node we can reach, right, from node u. And the third was that we were using binary lifting, right? We were pre-calculating by binary listing that from one step from u uh, to optimally reach to node v dash, right? So we were using binary listing, we were pre-calculating this, right? And the fourth was that we were doing a binary search type that from node u we if this is v, so we are checking if we are surpassing, that means we need less step, and we if we fall back we just think that that at least this much step will taken, so we will storing that distance, right? Suppose it did as, and from here we again check how many steps are needed, and we were adding that too, right? and and that was the whole crux of this question, right? Let's go and see the code of this one. So if you see the code of this, so we are doing the same thing that as we have discussed. That so we are making our temporary vector to store to sort the nums I and preserving the indexes, right? So we are storing in the pair of the nums I and its index, and we sort them, right? And we are making a vector map, vector MP, right? So to store that, we are storing the original index that was IDX, and what is the its index in the sorted listing, right? In the sorted list, and we are taking size as 20. That at max in 20 we can represent the all the largest steps we need to take. And here one optimization I have done, right? Uh, I will show you the previous course, right? I will show you the previous code, right? This is a little optimized one, and I will discuss that, right? So, so for to find out, right? To find out that here we were finding out now that from to where we can go up to which index, right? We can go. Let me qualify. So the things we are doing that from 2, right? It was 5, 7, right? So if max was 3, so we were checking out 2 plus 3 is 5, right? We can go up to 5, right? So we are just doing the same thing. We are checking suppose it was 5, 5, right? So it can go up to here. So for this condition, what we are checking, 2 plus 3 is 5. We are checking upper bound of uh, 5, that is 6. So upper bound will always return the index that was greater than this. So the upper bound will return this index 7, and before that index that will be valid. So we are doing IT minus 1, that last index, and we are storing for this, right? So this code is to get the from ith node at max at which node we can go up to, right? And here for every uh, value we are making our binary lifting table, right? So what we are doing, it is to the power I, right? So it is the I is the power, right? And this is a node. For every node we are calculating that from node, that u node, taking the I to the power I steps, right? I is 1 means it is to the power 1, then to the power 2, right? And from taking from that we are taking the half of that. For the 2 we will to to reach from u4, right, to the power 4 steps. We firstly take to the power 2, that means half step. We take 2 steps from u, then the node will reach, right? That will be u dash here, right? And from that node we are going to step further. So total we reach, are able to calculate 4 steps, right? So this is O of 1 we are able to calculate, right? And here for the each queries, we are getting the index in the sorted order. What is the index of the node in the sorted ma- list, right? The both uh, the source and the target, right? If source is greater, so we will swap that, because our string is stored in sorted manner. So from actually, uh, since we are considering that from 2 we can go up to 5, right? But since it was the directed edge, right, we can also go 2 to 5, but we have stored like this only. So what we'll do, if it is u comma v is coming as 5 comma 2, so we can just swap this 2 comma 5. The answer will be same as 2 comma 5 or 5 comma 2. So we are storing that. So that's why we are swapping. And if the U and V is same, so from second node, you want to go to second node only, so that will take only 0 step at to the power 19 step. We are still behind the V. That means we are not able to reach V, right? So for any, if we see here, if 2, 3, 4, 5, right? 10, 12, and max dif is 3, right? So if you say that it points to it points to 5, right? And from 5 is 5 points to this. So if you take one step, two step, and three, four, it will revolve around to the power 90. And if we are checking that 2 and 10, right? 2 and 10. So if you, even if you take to the power 19 step, it will be only revolving around this, right? It will do like this only. So every step will reach, to 5. You will never surpass 5. So your up you to the your 19, that is to the power 19, will be only 5 only, right? Which is less than your target. So you cannot surpass the target. You are not going beyond or on the target. So you cannot never reach that, right? So that's why we are pushing -1, that we can never reach. And now if we see that from 18, we are just calculating. If we take 18 and if we are falling behind the target, that means that if we are taking from 2 and our target is 5, and taking one step, we are behind, we reach 3, right? Which is behind 5, our target. So we need at least one step, right? And we take that step and we are updating you here that now calculate from here, right? So we are doing that if it falls behind the target, we are just adding. So this is 18, right? And 18 is at the power of 2, so we have to add as to the power I, right? So we are doing the left shift, that will add to the power I, right? And we are updating our u to up I, that now you calculate from there. That many steps, this many steps we have traveled, and we have updated our I, right? And if this is not case, then it will be greater than the V, means is fall when there is no, it will, if that's no case, not case, then it will fall behind our target. If it fall behind our target, so there is no need to take that many steps. We can reach there in less steps, so no need to take. So we simply ignore that one. So else we not need. And and after doing this things, we will be just behind our target. So we are adding distance +1, right? And the optimization I did was, since to find from 2 to 5, right? So from index 2, right? From this index, we are calculating now the max diff was 3 from what is the index of the 5, right? So we were doing upper bound binary search, but there is no need to do binary search, right? We can see that if it was 2, 3, 5, right, and 9, 10, 12. So if you see that we can take I and j 0, right? If you see that for two, and suppose max diff is 3, right? Max diff is 3. From 2 we can reach up to 5, right? So as for 3, it will be never less than 5. It will be either 5. If it was max, it was 4 also, right? So for 4 also, it will either it will be 5 or it will be beyond 5, right? Suppose here was 7, right? So it was either 5 or it was greater than 7. So what we can do, we can just take two pointer and we this was where I, and we will just increase increment our j such that the difference of the num psi, right, and the nums j is less than equal to max, right? We can just do and it will reach 7, right? So when will it be 7? So we will just store j minus 1. So up to this index, this is our target index. And when I will come, we will just check the same condition. If it's not, we will do j will be incremented, right? And we will store. So there's no need to do binary search by two pointers. Also, we can store, and that's the whole idea of that. And that's optimization I did here, right? See, so that is the optimization here. We are doing that. We are taking J0, right? And we are just, while this condition is true, we are incremented our J and we are just updating that, storing that it can reach up to J minus 1, right? So that was the code. If you don't understand the question, do a dry run and try to understand. And if you don't understand the binary lifting, right? So you should do for the understanding of binary lifting. Binary lifting is used in so many concepts in the graph, right? I told that it is same as the sparse table in we use, right? Sparse table we use in the range query of array, right? Range query of array. The same is the binary lifting in graph, right? For the range queries, we use binary lifting. So it is a very good concept to learn. And if you say the standard problem, that is the case ancestor, right? Case ancestor of node, right? So to find out the case ancestor, uh, it is used, right? Binary lifting is used. And there's one more good question to do, that is to find the distance between two nodes, right? Two nodes in a tree, right? In a tree or graph, right? And where we do this one, right? To find out the LCA, we use that. To find the LCA also, we use binary lifting. And the same concept in binary lift, to find LCA, what we actually do that for any node, the same concept. We try to from any given u comma v, we try to take to the power highest power. From highest power, we it will reach the sum ancestor, right? Then we decrement that to 2 or 7. If I take lesser power, can I surpass my ancestor or not? And by doing this, it will reach just below the ancestor, right? And just you will from there you get its parents, and that is your ancestor answer. So LCA is finding LCA is also a good application of binary lifting, right? So you can also try this. So that's all for today. Thank you.